In electrical engineering, a protective relay is a relay device designed to trip a circuit breaker when a fault is detected. The first protective relays were electromagnetic devices, relying on coils operating on moving parts to provide detection of abnormal operating conditions such as overcurrent, overvoltage, reverse power flow, overfrequency, and underfrequency. Microprocessor-based digital protection relays now emulate the original devices, as well as providing types of protection and supervision impractical with electromechanical relays. Electromechanical relays provide only rudimentary indications of involved phase and zone targets. In many cases, a single microprocessor relay provides functions that would take two or more electromechanical devices. By combining several functions in one case, numerical relays also save capital cost and maintenance cost over electromechanical relays. However, due to their very long lifespan, tens of thousands of these silent sentinels are still protecting transmission lines and electrical apparatus all over the world. Important transmission lines and generators have cubicles dedicated to protection, with many individual electromechanical devices, or one or two microprocessor relays. The theory and application of these protective devices is an important part of the education of an power engineer who specializes in power systems. The need to act quickly to protect circuits and equipment as well as the general public often requires protective relays to respond and trip a breaker within a few thousandths of a second. In some instances, these clearance times are prescribed in legislation or operating rules. A maintenance or testing program is used to determine the performance and availability of protection systems. A current transformer, CT, is a transformer that is used to produce an alternating current, AC, in its secondary which is proportional to the AC current in its primary. Current transformers, together with voltage transformers, VTs, or potential transformers, PTS, which are designed for measurement, are known as instrument transformers. When a current is too high to measure directly or the voltage of the circuit is too high, a current transformer can be used to provide an isolated lower current in its secondary which is proportional to the current in the primary circuit. The induced secondary current is then suitable for measuring instruments or processing in electronic equipment. Current transformers also have little effect on the primary circuit. Often, in electronic equipment, the isolation between the primary and secondary circuit is the important characteristic. Current transformers are used in electronic equipment and are widely used for metering and protective relays in the electrical power industry. Like any transformer, a current transformer has a primary winding, a core and a secondary winding, although some transformers, including current transformers, use an air core. In principle, the only difference between a current transformer and a voltage transformer, normal type, is that the former is fed with a constant current while the latter is fed with a constant voltage, where constant has the strict circuit theory meaning. The alternating current in the primary produces an alternating magnetic field in the core, which then induces an alternating current in the secondary. The primary circuit is largely unaffected by the insertion of the CT. Accurate current transformers need close coupling between the primary and secondary to ensure that the secondary current is proportional to the primary current over a wide current range. The current in the secondary is the current in the primary, assuming a single turn primary, divided by the number of turns of the secondary. In the illustration on the right, I is the current in the primary, B is the magnetic field, N is the number of turns on the secondary, and A is an AC ammeter. Typically, current transformers consist of a silicon steel ring core wound with many turns of copper wire as shown in the right illustration. The conductor carrying the primary current is then passed through the ring. The CT's primary therefore consists of a single turn. The primary winding may be a permanent part of the current transformer, with a heavy copper bar to carry current through the core. Window-type current transformers, aka zero-sequence current transformers, or ZSCT, are also common, which can have circuit cables run through the middle of an opening in the core to provide a single-turn primary winding. To assist accuracy, the primary conductor should be central in aperture. CTS are specified by their current ratio from primary to secondary. The rated secondary current is normally standardized at 1 or 5 amperes. For example, a 4000, 5CT secondary winding will supply an output current of 5 amperes when the primary winding current is 4000 amperes. This ratio can also be used to find the impedance or voltage on one side of the transformer, given the appropriate value at the other side. For the 4000, 5CT, the secondary impedance can be found as ZS equal NZP equal 800 ZP, and the secondary voltage can be found as versus equal NVP equal 800 VP. In some cases, the secondary impedance is referred to the primary side, and is found as ZS equal N2 ZP. Referring the impedance is done simply by multiplying initial secondary impedance value by the current ratio. The secondary winding of a CT can have taps to provide a range of ratios, 5 taps being common. Shapes and sizes can vary depending on the end user or switchgear manufacturer. Low voltage single ratio metering current transformers are either a ring type or plastic molded case. Split core current transformers either have a two-part core or a core with a removable section. This allows the transformer to be placed around a conductor with a minimum disturbance. Split core current transformers are typically used in low current measuring instruments, often portable, battery operated, and handheld.